Okay, hi everybody. I hope you enjoyed your day so far. Welcome to 212 Computer Architecture, and today the plan is to discuss some introduction to the course, some basics, and the plan for the course moving forward. Before I start, do you have any questions? I hope you all can hear me well. And as I said, if you have any questions, if you want any clarifications, I would prefer you use your microphone, and you all, if you could turn on your camera, that would be excellent. I would prefer to see some of you. Okay, great, thanks. Yeah, my name is Puyan Jamshidi. Let me introduce myself. I am an assistant professor in the Computer Science and Engineering department. I joined in 2018. Before that, I was a postdoc at CMU in Pittsburgh. And before that, I was in London, at Imperial College London. And I spent some time in industry, in software industry, developing some larger scale systems. And here is the link to our website. And you can check some more information about what we do beyond teaching. I also do research specifically at the intersection of computer systems, AI, machine learning. I also teach a course on machine learning systems. Also, I teach AI 5AT. And in general, my research is on different topics in ML systems. For example, we have work on ML for systems, specifically, for example, optimizing performance. When we have a deep neural network, we want to deploy it on some embedded hardware, some resource constrained environment. So this is one of the direction in research that we do. We also do some research related to autonomous systems. More specifically, we have a project with NASA making a space lander autonomous by using some basically research at the intersection of planning, machine learning for perception, and also adaptive systems. We are also active on the theory side of machine learning, specifically causal AI. You might have heard about it or not. And one of the exciting research that we recently started 2 years ago is in the area of adversarial machine learning. Specifically, we developed a framework, it's called Athena, for defending machine learning systems. But if you're interested to know more about these, you can check it out and see what we are doing. Okay. So some housekeeping information about the course. We will have some course websites soon, hopefully this week, at this link. Still, I'm building it up. I hope that you have received basically an email about Piazza. I automatically sign you all up on Piazza. We use this as a tool for communication. Specifically, if you have some questions about homework, project, any assignment, or in general, if you have any question about the course, I would recommend to ask your question there. Please don't email us. Only email us if the question cannot be asked in public. So I would prefer you ask your question here on Piazza, and it is for a reason, because like maybe some of your classmates can answer the question, you can learn from each other. These questions typically are very useful for all of you. And essentially, specifically, I mean, I use Piazza for all of my courses, AI and machine learning, and students tend to like it. And specifically at this time, the COVID time, when the lectures are all online, this is a way for you to know each other, to build a community and learn more effectively from your peers. And this is very helpful. We also plan to use Gradescope for the assignment. I also signed you up on Gradescope. Probably you did not receive an email, but you're already there. So once we post the assignment, you will automatically should receive email about this assignment. So we use Gradescope for any homework throughout this project, throughout this course. Any questions so far? If you need any clarification about this, please let me know. This is the time. We have also a TA, Norris, helping with grading stuff and also answering your questions. If you have any, again, I would like to emphasize on using Piazza rather than email. This is a lot more effective and more useful for you guys. And this is his email address in case if you want to contact him. And you know the lecture time. We also use Zoom, and all lectures will be recorded. So these will be available. I will share the recording via Dropbox link. Probably I will also share it on YouTube. So let's see how it goes. And yeah, throughout the lectures, I would prefer to see you as much as possible, so I can get this feedback that I always get from students, whether they understand the concept or not, that they can follow me. Okay. Also, we have a recommended textbook for this course. This is a fantastic book. I highly recommend it, even though it's not required. You don't need to buy it if you don't have it. The library should have some copy. But this is a fantastic book, specifically if you want to learn more in depth about computer architecture. In particular, we will cover chapter 6, 7, 8. So these are basically related to architecture, microarchitecture, and also memory. I'm not sure whether in this course we get the chance to cover the memory or not, but we will see. It really depends on the pace that we go throughout this course. But essentially, you should be good to learn about computer architecture and do well in the exam. If you follow the lectures and do the homework, we'll also have projects. The book is only recommended for you to know more about computer architecture. It has also some chapters about digital design, which you already know about it, or at least I presume you already know about it. This basically we have some quizzes throughout the semester. We have some projects, midterm and final. More detail will come later, but this is a rough also basically percentage of your final grade that are associated with each. As I said, we also have a research group, AICs, which we work on some learning-enabled autonomous systems. And these are by graduate students, fantastic graduate students, working on different topics that I mentioned, basically. Okay. Let's start about this course, computer architecture. So essentially, computer architecture is one of the unique courses in computer science, which basically you get the chance to know how computers essentially work from ground up. You can write program already with using different languages, maybe Python, C, I don't know, Java. But computer architecture is one of the courses that you get the chance to know behind the scene, like how actual computers actually work behind the scene at across the stack, not only at the software level, but across the stack, also at the hardware level and middleware. So essentially, at the end, we want computers to do some computation, right? That's essentially the function of every computer, to do computation, right? To solve some problems that we have. These problems, you're familiar with it already because you took some algorithm courses, right? You're given a problem to solve. Essentially, these problems are well specified using a specification language, which you might have heard about it, or at least with English, right? You have some description about this problem you want to solve, right? And then the goal or the key aim of doing solving this problem essentially is to gain some insight. So we have some difficult problem to solve. For example, we want to find how to cure a disease, like how to find a cure for coronavirus, right? Or we want to calculate a very very difficult mathematical problem. Essentially, throughout, even if we may not be able to find a direct solution for this problem, at least through computation, we are able to gain some insight. That's one of the important aspects of computation, essentially one of the motivating aspects of computation. It is, and maybe through AI or more sophisticated type of computation, we may be able to find the actual solution as well, and maybe have a better future and life, right? But beyond these high-level stuff, like at the end of the day, computers only deal with electrons, right? This is what they understand. Because computers are all about the actual hardware, right? This is like at the bare metal. This is what they understand. The very bottom of the layers, right? So essentially, if you ask, okay, maybe it's better to write or to talk with these electrons directly. I mean, this is difficult, right? It is they follow some physical laws. This is what they only understand, right? And it's really difficult to, or even impossible to talk directly with these electrons. But then we want to, in order to do some useful stuff, we need to build some layer of abstraction, right? So again, if we want to formalize this, you have some high-level description of the problem. You already have taken 145 or 206. So you have some knowledge about, some language like Java, C, or somehow programmer's view of a computer system, right? So at the high level, you are able to program and solve this problem, right? At the bottom, you have some digital logic as a sort of model of computation that you have learned in 211. So you know already how to design a circuit, right, with this digital logic. So essentially, this view is the hardware perspective of a computer system, and these two are essentially two different views, as you already have experienced. When we write program at a high-level language like C or Python, we don't care about like how these things get executed like at the circuit level. Because if you want to think about it like, I mean, it's really inefficient way. And that's why we have some high-level languages like Python. And like if you want to solve a difficult problem using like low-level stuff is also sometimes is even impossible, right? To design something based on these circuits directly. So essentially the aim of this course is to understand what's going on in between. And that's why it is, this course is important. Essentially, we want to learn how we can have some maybe lower level languages like assembly that we can translate our high level program to low level digital logic at the hardware level. So essentially, filling the gap between these two different perspectives that you're already familiar with, and how computer essentially is designed using these logic gates and wires, right? Essentially to satisfy the goals that are somehow we want to achieve through some high level programs, right? So the architect point of view, top level again is the programmer's view. Down is the hardware designer view that you already got a chance to know about this. In between is the architect or micro architect point of view, which cares about how to design a computer that meets the system design goals, right? And for system design, we might have really different goals. Sometimes we care about performance a lot. Sometimes reliability, security becomes very critical. And understanding these design goals, making trade-off at these design goals, at the level of these design goals, is what this course is about. Essentially making these choices are the most critical role of the computer architect, that they need to play, right? Making this trade-off is one of the fundamental and most important role of these architect. And you will see some specific example, get a better understanding of what I'm talking about now. Do you have any question about this? Is any one of you didn't have these two courses? Any of these two courses? Hopefully you all have taken like these prerequisite of this course, 145 or 206, essentially programmer's view, and also 211 about digital logic design. Do you guys have problems seeing the slides? I see in the chat. Do you see the slides all right? Okay. Yeah. So let's also talk about this transformation hierarchy. Essentially, what is going on in between, right? So at the top level, we discussed that we have problem. At the bottom, we have some electrons that they follow the physical laws. And then we want to fill in the gap, right? So we have some layers in between that essentially, for example, once we have a specification of the problem, based on this specification, we can write algorithms that realize or implement this specification, right? And then like algorithms for running algorithms, we need to write them in a specific programming language. Could be like any of these programming languages that you're familiar with, right? High level thing like Python, or like lower level programming languages like C. Essentially, you need some programming language to realize algorithms, and some system software sits in between in order to run essentially the algorithm. And then you have some interface, right? So this is where low-level stuff or the architecture aspect start, right? So you need some software-hardware interface that acts as a translation or some concrete contract that basically enable these layers to talk with each other without disrupting the whole system. And you can think about this software-hardware interface as, again, some contracts. We'll talk about it in detail about the specific ISA, right, or instruction sets that define these contract. And then, like, somebody needs to realize this contract at the hardware level. This is it's called microarchitecture. Microarchitecture is specifically a realization of these contract, these instruction set that are defined in between. So instruction set essentially are these abstract level that you can realize it in different way, right? So for one instruction set, you may have realization, like many different realization based on the goals that you have, right? So for example, you can implement an ISA instruction set to gain like performance. Sometimes you have totally different goals, right? So you might care about reliability more. So essentially with these goals, you can have different realization of these, which is called macroarchitecture, essentially, and we'll talk about this throughout this course. And then down for implementing macroarchitecture, you need some logic. And for implementing logic, you already know in this previous courses that you need some like devices like transistors to implement this logic at the very low level, right, at the transistor level. And then like transistor follow the physical laws, right? So change of voltage, this is what they how they work, right? So this is all layers that we need. Essentially, this is the computer architecture viewpoint, or at least the traditional way of what we call computer architecture. So talking about like this contract, this instruction set, or software hardware interface, and also how we are going to realize this contract, this software hardware interface, is all about like traditional view of computer architecture. But now this viewpoint has broadened up for some reasons, specifically due to new applications that we have, right? For example, for some domain-specific applications, we now see the appearance of a specific accelerator, like, for example, AI accelerator, machine learning accelerator, accelerator for genomics, like accelerator for self-driving cars, for example. Due to these new applications, basically very domain-specific accelerator appeared, and like for this, we require to have a broader understanding of computer architecture, and that's essentially the expanded view of computer architecture, which has become much more important than the traditional perspective that was associated to computer architect. Now, essentially, what it means is that the implication of this broadened view is that, like, whoever played the role of computer architect needs to be aware of, like, the high-level stuff, the algorithmic part specifically, and also, like, obviously the lower level stuff at the device level. Essentially, as a specific example, if I want to provide, but I will go into the detail later on, like for machine learning systems, like for specifically deep neural network models, you know that these are mostly at a mathematical level, matrix multiplication. And there are these matrix multiplication, this kind of computation is very expensive if you want to run it on traditional hardware, because you need to load many weights of the network from the memory to do some computation in the CPU, and this loading weights is a very expensive operation. But now people are working on designing a specific hardware that with this new hardware paradigm, with this new architecture paradigm, you can do computation near the data. You don't need to load the data into CPU. You instead go and, like, do the computation inside the memory. We'll talk a little bit more about this later on, but this is what is called the broader view of computer architecture. Why? Because the computer architect needs to know about the specifics of these algorithms, needs to know that know about, like, the mathematics behind these machine learning algorithms, that like what kind of operations, like they do, like matrix multiplication, and you have a lot of, you know, memory access and so on. You have a specific patterns in computation that can speed up the process by orders of magnitude, which otherwise you could not ever gain it by any sort of optimization at any level of the stack on traditional hardware. And that's why it is important to broaden this perspective. But essentially, within this course, even though we'll talk a lot about like the other layers, but our focus is essentially the traditional perspective due to limited time and the scope of this course. I'm going to only focus on the these two layers, and from time to time I will talk about specifically some domain-specific computation as well, specifically in machine learning, which is my interest and research. So I will try to connect it with a broader view, but due to the time restriction stuff, we cannot like cover the whole layers of the expanded view. Okay. Do you have any question so far? I hope these are clear for you. Basically the purpose of computing I mentioned is gaining insight, was mentioned by Richard Hamming, which you might know, and we need to gain and generate this insight to solve problems essentially, and basically, so I already talked about this. We need to fill these layers in between to be able to solve this problem. I already talked about this perspective. Okay, essentially, computer architect perspective is computer architecture is essentially the science and art of designing a computing platform, right? From all the way hardware, interface, system software, and programming model. We essentially have some design goals. And these design goals are different. Like sometimes we care about performance on very specific type of workload. Like sometimes we want to design a computing platform to only run scientific algorithms. Sometimes, no, we want to design a computing platform that maybe run our car, right? So these two are totally different, right? For the scientific computing, performance matters because we want to get the result, find the solution as soon as possible. For the car, reliability matters, right? So we don't want to basically the car crashes because its computer like failed. So essentially, sometimes like the goal might be the cost as well, right? So you have some constraint, like for example, for the space lander that we are dealing with, we have some resource constraints, right? We have limited battery, and we want to do some scientific exploration in a space with this limited battery. So designing a computer system that achieves these goals essentially is important, and like different systems again comes with different goals. So it's not general purpose essentially. And in this course, we'll talk about like many of these systems, so you get some concrete idea about these specific different goals and how to make trade-off in order to design a system that satisfies these goals properly. And sometimes, yeah, you want to get the average performance on across all known workload, and this is what we have. Essentially, this PC general purpose computers that we have are designed to get the average performance on all known workloads that we may want to run on these computers. Yeah, some specific example, in this case, for designing mobile, again, mobile is a computer system, right? The goals are totally different than PCs because mobiles are connected to battery, right? PCs are connected to power supply. So you totally have different design goals when you're designing these systems. For drone, again, you have some other goals, like it has to be agile, right? It should not, with a specific weight, right? Also, battery constraints here matters a lot. For this, again, for self-driving car, this is one of the earlier version of self-driving cars. Again, the goals are different, right? For self-driving cars, essentially, reliability matters a lot. For like data centers, essentially, also another type of systems, computing systems, right? Some data centers, you want to get a specific workload. Some you have general purpose workload. Like, for example, here, this is, I guess, Google data centers. So you want to run many different applications, right? Gmail, some cloud applications, some ML for recommendation systems, and so on. For some other data centers, you might have only like scientific computing kind of algorithms running, right? So, for example, for sequencing genome data, like, again, like, even at the data center level, you might have different goals. For machine learning, this is like example of TPU, Google TPU, that has been released like several years ago. The first version was, I guess, 2017, mostly for running or doing inference for neural network. Again, this is, as you see, this is a very specific type of architecture. It's called systolic arrays. Hopefully we'll talk about it at some point. These particular type of architecture, even though has been proposed like many years ago, but was not really popular since machine learning gained some interest, and this is one specific realization of systolic arrays. basically doing computation for deep neural network, doing inference, essentially matrix multiplication type of computation. And here it's an example of another system for Tesla, right? This is the computer that they have designed for their cars, right? Here you see that they have two specific microprocessor here. Again, the reason is clear, because if one of these fail, the whole car would not crash, right, as a result. So still, you can do some computation if in case one of these failed. So here, obviously, redundancy basically happening because the design goal here is totally different. Reliability matters for self-driving cars, even though for other type of computation may not, right? Even if you fail in one inference, maybe you can repeat it again. Again, different computer systems have totally different design goals, and as a result, you see different, and that's why you need different system. And that's why Tesla doesn't want to use normal computers in their cars, right? So they have a specific goals, performance, reliability, that for which they need to design these systems. Okay, and that's why we need to have this expanded view in order to design such systems. And this is essentially called co-design or software hardware design, where you don't go design the hardware without having software view in mind, and also you don't go design software without having the hardware view in mind. And that's why it is really important for you guys to understand this perspective, because this role, and essentially I noticed it recently after, again, these applications like AI, ML became more prominent. How important this is for students to understand the whole stack, to have a better understanding of the whole stack, right? Essentially, those who want to work on the software, the higher level of the abstraction, it's always good to have an understanding of what's going on in between. If they want to design an algorithm, they can design it that exploit the best features of the underlying hardware. And also for those who wants to work on the hardware side of things, is good to have understanding of like different type of workload. Like these workloads essentially they have totally different requirements. Like the workload that you see for recommendation system is totally different from the workload that you see for like for email, right? So these type of workload essentially provide opportunities for designing better system that satisfy some important goals that people care about. And hopefully throughout this course, at least you guys get a better understanding of this perspective. Okay, any questions so far? You're good? Okay, so let's also talk about few things that's happening today in computer architecture. Some maybe research going on at the research level, at least to motivate you why this course is important, right? And again, like I talk about like a couple of different research directions with different objectives, right? Like one direction again is about performance and energy efficiency, right? Which I talk about it, right? Again, like we talk about this Tesla computer. And by the way, like if you want to know more about the design of this system, you can watch this video. They talk, the designer of this chip talk about some detail, some of these performance metrics and also why they needed to, in first place, they needed a new system and how they design it to some extent. And for what kind of workload it is useful. As you know, Tesla doing a lot of machine learning as well. They do sensor fusion. They do a lot of like neural network stuff for generating some signal for their self-driving component. So a lot of, I mean, beside redundancy and reliability, also they're also doing a lot of, you know, parallel, like for their machine learning pipeline, specifically these matrix multiplication stuff. They make it very efficient for ML workload and particular type of ML workload that they have. And also for the TPU, and this is also the newer version of TPU, which is designed not only for inference, but also for training ML models. And like these type of TPUs are used in Google data centers for training their ML models, and they have like again some specification, as you see on the right hand side, right? In terms of number of floating point operations that this chip is able to perform, and some other specification. But essentially, the idea behind this type of design, this type of computer architecture, dates back to 80s. You see in this paragraph as well. So this is this type of architecture is called historic arrays, has been proposed in 80s, but never been popular until now, where ML type of workloads gained a lot of attention. Like in 80s, like ML was not popular, at least was not used at a scale that is now being used like for many applications, right? From large scale application to even like in our mobile or our watches, these type of models are running. But at the time, this type of workload definitely was not the primary type of workload out there, and that's why this type of architecture has never gained such attention that is now happening, right? So and now this type of implementation, these TPUs are used at a scale, at least in Google data centers around the world. And down, like I don't want to go into the detail, but the key part of this design, this computer architecture design that you see in this slide, is this unit that that essentially do some calculation for matrix multiplication, and also some other computation that you need for deep neural network, like activation, normalization, pooling. So it is essentially this type of chips has been designed for like neural network type of workload, not general workload. I mean, you can run general workload in these TPUs, but like they're not efficient. Like you don't gain efficiency as you expect for other type of workloads. This type of computer architecture, this kind of computer system has been specifically designed for particular workload, essentially in this case neural network, not even like other type of ML workloads. And this trend like is not only for Google or Tesla, other companies also pursuing this type of domain specific computer architecture design, and it's everywhere now. So this is like why, again, another reason why it is important. Another thing, another example is it's called I mentioned that to you a few minutes ago, that, for example, this is a traditional, and we will go into the detail of this type of architecture because this is fundamental. Like this is von Neumann type of computers that you have memory, processing unit, and control instruction for fetching instruction from memory, doing calculation in processing unit, and storing back the data. So for example, if you want to compute a function over some input like A happens to be a matrix, right? This is the way how you need to do it. Like you need to fetch a lot of data out of memory and store it back. And this becomes a bottleneck, specifically if you want to fetch a lot of data. And for calculating f of a, this is very basically has a lot of overhead and could be slow and like inefficient in terms of energy specifically. A new paradigm is called basically in-memory computation, which is like a state of the art for like for some workload, right? Specifically again, neural network stuff, where instead of fetching memory, you do calculation inside the memory, and for that it's called computational memory. Essentially, you do calculation inside the memory by some like physical laws, specifically in the case where you can construct these memories with analog devices, and you gain orders of magnitude higher efficiency with this type of computation, because in this case you don't need to fetch data back and forth. You compute f of a there, and you store it back there in the memory. So you do it a lot faster in this case. But obviously this is not designed for a specific, for general workload. It makes sense to do this for very specific type of workload. Yeah. And yeah, the key reason here, like when it comes to memory, is that like every memory access is very expensive, right? So if you want to access local memory per word, you need to pay 5, for example, in this case, picojoules, right? But if you want to do even on cheap SRAM, the SRAM that is not local but still on cheap, you need to pay 1 order of magnitude higher in terms of energy efficiency. And if you go outside CPU, you see that it is already 2 orders of magnitude higher for every access. And think about it, like when you have a matrix which is large, you cannot obviously store the whole thing in local memory to do this computation fast. You need to go back to external memory and fetch the data back, and this becomes very expensive already, right? But on the other hand, like you can do this again, as I mentioned, like in memory, doing some exploiting the massive parallelization of this type of architecture without even moving data anywhere. Also, beyond performance, like these examples that I mentioned was about performance. But beyond performance, sometimes reliability and security matters, right? For example, in this case, people have shown that you can access memory in a very specific way, and you can flip the content of a memory. For example, you can flip a bit from 0 to 1 or 1 to 0 with some predictability, right? And people have shown that this is really happening in most of the realization of the memory that we have out there, and it's very simple. It's very simple idea, in a way that, like, for example, you know that, like, part of the memory you have access, part of the memory you don't. The idea is that you access part of the memory that you can access, you access it in a specific way to force part of the memory that you don't have access to flip. And once this flip, then you can go and, like, you already, for example, let's say part of the memory that says that, okay, only those who have root access can read this. If this is 1, for example, right, then you cannot read it. But if you force it to 0, then you can go and read it, right? So this forcing part of the memory by just reading from the other part which you have access is essentially have some security implication. Specifically, for example, let's imagine that you have access to this row, you can read it, you can apply a high voltage, you can open it and read it. This is the way how you read part of the memory, right? And then you can close it, and then you can read it many times, right? If you do this with a specific pattern, you can force the other rows which are nearby to flip from 0 to 1 or 1 to 0. And then with this way, you can do some hack into the system. You can gain some access to the system that otherwise you never had before, and you can do some malicious, access to the system that you should not have access to. So, like, it's called hammer row, which and you can read about it in this paper. It's a very simple idea and very simple implementation, but, like, had massive implication for the computer architecture community. And they show that it actually works in, like, many different for many different memory vendors with a high probability. The other example is about Meltdown and Spectre, which you might have heard about it. It was in the news a few years ago. And again, this this vulnerability came from the very specific way your program is running on the hardware. Essentially, this vulnerability came as a result of very specific execution of instructions. The way how CPU run instruction and use cache in order to store some data, and then others could exploit the content of this cache in order to gain some access or do some malicious act to the system. But I don't want to go into the detail, but essentially the malicious program could somehow inspect the content of the cache in order to infer some data which is not supposed to have access to. This was like this vulnerability was not really easy to do, and but again was very widespread, and they showed that in almost all microprocessor this vulnerability exists. And this could be like could be nothing for a specific system, but could be very dangerous for other type of mission critical systems. And if you want to know more about it, maybe read about this blog post, Project Zero. They have some very interesting information in there. It's called like it's called a side channel attack, where you can infer some very useful information from the cache, content of the cache. Again, so to summarize, we are almost there. There are some interesting directions in computer architecture going on, from new computing paradigms, as I mentioned, from in-memory computing, neuromorphic computing, secure and dependable computers, to also new accelerator that I mentioned about, like machine learning, also some graph analytics, genome analytics stuff, which we did not talk about, and also some direction in research of designing intelligent memories and storage systems, mainly to again improve performance for particular type of workload, again mainly AI systems. So this area is the area of computer architecture is important. Hopefully this gives you some reason why this course is important, and why you need to learn as much as possible in this course. And yeah, let's stop here, and we'll continue on Thursday. If you have any question, I will stay here for a few minutes. I would be happy to answer any question if you have. Thank you.